piece today. And please join me in welcoming her.
Great, thank you. Oh, thank you. Thanks very much for that nice introduction, and thanks for having me here. I was here actually 5 years ago at the beginning of my first postdoc, so it's really nice to come back. Before then, we didn't have any gravitational wave detections of binary black holes or neutron star mergers, so the field has changed even in that time scale. I'm really excited to share with you some of the latest results. So as the title suggests, I'll be talking about neutron star mergers, both the local population of one that we have, or actually two, but mainly focusing on the first one, the first neutron star merger detected by LIGO, and then connecting them to the properties of cosmological short gamma ray bursts, which we think also come from neutron star mergers or neutron star black hole mergers. And this is a beautiful Hubble Space Telescope HST image, 7.5 hours of exposure time at the site of GW72817, the first neutron star merger. This box indicates the location of where the neutron star merger occurred. And you can see for the first time since the merger, there's no more optical light at that. So this actually provides a really nice template image. And I'll talk a lot of the talk will be centered around results from this image. So this is a really nice local merger, a beautiful galaxy, lots of structure that you can see in the image. But for the past 10 years, we've been also studying these types of events just at cosmological distances called short gamma ray bursts. So this is actually my reality in a lot of cases. These are the types of galaxies I study. This red circle indicates where the short gamma ray burst occurred. I'll talk about the afterglow emission. Sometimes we see kilonovae associated with those too, but these are the types of galaxies I typically study and the types of redshifts that I look for. So I'm interested broadly in connecting the two populations. Feel free to ask questions too throughout the talk, if you have any. So just zooming in on the system, I'm sure many of you are familiar, being a hotbed for nuclear physics research here, but I wanted to just give a primer for anyone who hasn't seen this in a while. So we have two neutron stars, they're merging, they give off gravitational wave radiation. Also, you can have a neutron star and a black hole too, and the new observing run of LIGO has actually seen that for the first time. Any neutron star involved binary is expected to produce electromagnetic emission. And so during the merger process, you have ejected material, neutron rich, that produces the beautiful heavy elements that we now know about. The two neutron stars merge, they produce probably a hypermassive neutron star with a collapse to a black hole. That central engine powers a relativistic outflow, and that's called the gamma ray burst. It's called a short duration gamma ray burst because the very high energy gamma ray emission lasts for a very short period of time, so less than 2 seconds or so. And so these short duration gamma ray bursts, we've been able to actually see these down the barrel of the jet for the past 2 decades or so or more. And now for the first time, we're starting to see this kilonova emission. It's important to actually map this across the electromagnetic spectrum because each process dominates in a different wavelength or different color. So these are, even though they're called gamma ray bursts and they're called neutron star mergers, they're extremely colorful displays of light across the EM spectrum. So the kilonova, as you may know, dominates in the optical and infrared emission, whereas this relativistic outflow, this gamma ray burst, dominates in broadband, so across the EM spectrum. So this is, I'll go into more of the details of the physics in this outflow. It's essentially synchrotron emission emanating from the radio to the X-ray wavelength. So we, in principle, can see it across the EM spectrum. These are very colorful displays of light. I'll be mainly focusing on the relativistic outflow portion, as I know you've probably been inundated with expertise about the kilonova. So I just wanted to provide kind of some new expertise and an update on its evolution. So broad motivating questions that kind of guide my research and you can kind of think about throughout the talk. These are some major unknowns in our field. I'm interested in what conditions lead to the formation and evolution of neutron star binary systems, formation and merger. How often do they occur? So it's they're actually pretty rare occurrences in the universe. So for every 1,000 supernovae, core collapse supernovae, there might be one neutron star merger or one neutron star black hole merger. But pinning down how often they occur, even if they're rare, is important for understanding the evolution of binary systems. And finally, what, of course, one of the hottest topics, what can we learn from their electromagnetic outputs? As I've shown you, seeing them in all colors can tell us a lot about the physics of these explosions. So this is really an observational golden era to make progress on some of these questions. And so this is an artist rendition of a gamma ray burst. And you can see if you're staring down the barrel of the jet, we've been able to actually be sensitive to these on-axis short gamma ray bursts for a couple of decades now. The latest workhorse for localizing and detecting these is NASA's SWIFT satellite. So this has been in orbit since 2004. So it's now a 15-year anniversary. And we've been able to see this relativistic emission on axis and make great progress in our understanding of what the origin of short gamma ray bursts are. We now think, based on a body of circumstantial evidence, where they explode in the universe, what type of galaxies they occur in, where they explode within their galaxies, that they do in fact come from neutron star mergers. So this is a really nice avenue to explore neutron star mergers, but we're always kind of stuck with this vantage point. So LIGO has actually, one of the revolutions is that it's actually giving us a different vantage point of these neutron star mergers for the first time. It also is not as sensitive as gamma ray facilities in detecting these things. So it will, by default, detect mergers at very local distances. And so we can see them from a different angle. We also see them much closer, so we get a lot more information. And so LIGO is detecting these things for the first time off axis, and we're able to see the more isotropic emission components, not just that relativistic outflow, but the kilonova emission, and also the afterglow, but it looks a little bit different than an on-axis afterglow. So it's a really great era to make progress. Now we have, for the first time, 2 avenues, just as of 2 years ago, 2 avenues to make progress on questions of mergers. They also, as I alluded to, because of the different detection thresholds, they actually provide complementary discovery streams. So this is the redshift distribution of short gamma ray bursts from a collection of about 30, 35 or so that we have so far. You can see it's, for now, strongly peaked at about redshift half. You can just pay attention to the gray histogram if you're interested in the division between elliptical and star-forming host galaxies, and that information is provided. But you can see there's kind of a tail out to redshift 1, 1.5. Right now I'm working on a census to really fill in this gap and see if this is a real effect or if there is a population of short gamma ray bursts that we're missing just because we're not doing our due diligence and following up their host galaxies and getting redshifts. But suffice it to say, most short gamma ray bursts are detected at cosmological distances, whereas neutron star mergers detected with LIGO are, of course, at about redshift twiddle 0, so really, really, really nearby. And so LIGO at design sensitivity will find neutron star mergers out to 200 megaparsecs, which is redshift 0.05. And so you can see it basically is redshift twiddle 0 compared to the short gamma ray bursts we're seeing. So again, by connecting these populations, we're also connecting to populations in cosmic time too. So the outline for the talk, I'll focus mainly about 30 minutes on relativistic outflows, what we know from short gamma ray bursts, and then give you an update on the 2-year evolution, 2.5-year evolution of 1708-17. So these are based on new observations taken over the past year. Then I'll have a few slides each on constraints on the dynamical origin. So basically being able to constrain whether the neutron star merger from 1708-17 came from a globular cluster or not. So this has important implications for formation channels. And finally, talk a little bit about results from LIGO Virgo's 03 so far. There was actually a cool result on the second neutron star merger detected by LIGO released just last week. Okay, so first I'll concentrate on the relativistic outflows. So let's zoom in on what's happening from a neutron star merger jet. So we have the progenitor. It gives rise to a central engine, probably a transient accretion onto a black hole. That gives rise to a relativistic blast wave that gets shock heated and produces gamma ray emission. And that's why we call them gamma ray bursts. It's the first thing we see from gamma ray bursts, and so we call them gamma ray bursts. And that's called the prompt emission. And then the remaining portion of the outflow, the kinetic energy imparted and the rest of the blast wave interacts with the surrounding medium and produces synchrotron emission. So this is electrons being accelerated in a magnetic field, and that is broadband. And so I'll show you this, what a synchrotron spectrum looks like, but essentially it's featureless, but across 9 orders of magnitude of frequency on the EM spectrum. So these are actually very colorful displays of light, and this is what the relativistic outflow produces. The brightness and evolution of this afterglow depends on the kinetic energy imparted, as well as the density of the medium it's exploding into. So a brighter afterglow will be produced if you are exploding in a high density medium, for instance, or have more energy in your explosion. So we've been studying these for a long time and actually trying to map the entire afterglow spectrum. And so this is a toy synchrotron spectrum. And you can see if you actually map these in various frequencies, so for instance, in the radio, optical, near-infrared, X-ray bands, this actually maps the fundamental properties of the shock, of the explosion, and of the geometry. And so in particular, this can map to, if you can actually be lucky enough to catch the fading afterglow after a gamma ray burst or a merger, then you can actually, and then try to even get detections in each of these bands and then map its evolution over time on the very fast timescales in which these afterglows occur, then you can hope to understand the fundamental properties. So the kinetic energy, the density, what we call the microphysics of the shock, so the fractions of energy going into electrons and magnetic fields. These are fundamental parameters for understanding particle acceleration and shocks across a wide variety of explosive phenomena. And then also geometry. So how, every artist rendition I've shown you has like a relativistic jet. And we sometimes take for granted the fact that the outflows are collimated. But in fact, there's only been a few cases in short gamma ray bursts where we've actually seen evidence for collimation. And so you can think of if all mergers have collimated outflows, that means that we're, for the gamma ray burst population, we're only seeing the small fraction with their jets pointed at us. And there must be many more that are pointed away from us. And so that basically the collimation angles have implications for the energy or the event rates and also the overall energy scale. So that's a key parameter to understanding. So this is kind of motivating why we care about the relativistic emission to begin with. It tells us fundamental properties about the burst, the microphysics, and the overall event rates. It also, by looking on axis at these short gamma ray bursts, can tell us, can serve as inputs for the predictions of off axis signals. And so to try to understand, taking the on axis short gamma ray burst population, mapping their afterglows, then getting these parameters out and then using them as predictions for the off axis LIGO mergers is also another motivation to study these. So the key ingredients are rapid response and sensitivity. Of course, these are fast fading signals. They're also extremely faint. And so I always like to give a real world example of this. And this is really something that happened in real life. So this was not this past Thanksgiving, but the Thanksgiving before that. So this is just an example of what my life can be like sometimes. So I was at home in Rochester, New York. My dad was cutting the turkey. We had a beautiful dinner on Thanksgiving Day. It was great. And then that night, I got woken up at like 2 in the morning by a neutron star merger detected by SWIFT. And so this was a gamma ray burst, a short duration gamma ray burst. I got up. I had my cell phone blew up because I get text messages when this occurs. I determined it was a short duration gamma ray burst, so I was interested in following it up. My postdoc was actually awake and ready to trigger a telescope, so we triggered the Keck observatories to which Northwestern has access. We really wanted to pinpoint that afterglow in the optical band, and we got a really deep image and did. This is what I call a beautiful image of a, it's smooth and everything, but we see it's definitely there. And we were able to get on within a few hours. We sent a telegram to 1,000+ astronomers of our results. We pinpointed the afterglow. The sun rose and we got a few hours of sleep. And now we're working on a paper getting follow-up observations using that afterglow, not only its evolution over time, but also to pinpoint the location of it, to find to assign it to a host galaxy, and write a paper on this. And this one actually happens to be a particularly high redshift burst. So this is the afterglow, but the host galaxy is actually buried underneath this. And so we had to wait for the afterglow to fade to do anything. But this type of cycle basically, doesn't happen too often, but with gamma ray bursts and now also with mergers, this type of thing does actually interfere with real life sometimes. So why do we put ourselves through all that pain and basically dropping everything and chasing the afterglows? Well, the main open questions, now this is a slide that I showed you before, but in terms of understanding the relativistic emission, one of the main questions we can actually get at now is understanding the velocity structure of the outflow. So understanding whether there's just one uniform speed at which jets are launched, or whether there's some sort of structure stratification of the ejecta. So we're now in the process of being able to kind of constrain how the jet is launched and how it behaves in an environment. Another thing that's interesting is the kilonova emission, which is that neutron-rich material that's ejected prior to merger and during the merger. That can actually create a cloud of material that basically the jet has to punch through. And so you can imagine that the jet has to kind of punch through this, moderately dense cloud of material and actually break out. And sometimes that can actually imprint a signal on the actual structure of the jet, the velocity structure. And so the interplay between the relativistic jet and the kilonova is also a really interesting question to study. And finally, rate. So again, the geometry of this jet can actually give us an understanding on the rates of these events. So these are the fundamental questions we can now start to make progress on. So there's been early afterglow studies following short gamma ray bursts and doing this whole mapping of the synchrotron spectrum. You can see this is no longer just a toy spectrum, but an actual spectrum, and this is taken 12 hours after the burst. This was a burst back in 2005, and you can see by fitting synchrotron models to it, you can get properties like the kinetic energy and the density. And then doing that for a population of short gamma ray bursts, you can see this histogram of circumburst densities, and these are the black bars are short gamma ray bursts, and you can see they're all at very low density environments. So these long gamma ray bursts that provide this comparison sample are from massive star progenitors. So these are a totally different class of objects that have massive star progenitors. And so on average, short gamma ray bursts, because they come from neutron star mergers, they occur in very isolated environments and actually explode in very low density regions. And we can only get that type of information from the afterglow. So just to harp on that a little bit more, the picture I showed you on the title slide where you can see the short gamma ray burst exploded in a, basically quite offset from its host galaxy. This is actually a really important clue as to the origin of short gamma ray bursts, because if you imagine you have two neutron stars, each one receives a kick at birth. So basically when the neutron star is born, if the either the neutrino emission or the distribution of matter of the core, the explosion of the star is asymmetric, the resulting core collapse can also be asymmetric, or actually it goes the core collapse first and then the explosion. But in any case, it can actually impart a kick onto that neutron star. And so if you imagine that you now have two neutron stars that have to undergo that process, and then they get kicked, so then the binary system is traveling with some velocity. It also takes some time for the neutron stars to merge. And so that so-called delay time, merger time distribution or delay time, actually, while it's traveling, means that by the time we see them merge and explode as short gamma ray bursts, they probably will occur somewhat offset from their host galaxies. And so this it goes hand in hand with the fact that we also see them in very low density environments. We see them offset from their host galaxies. The picture makes a lot of sense that they come from neutron star mergers, at least this cosmological population. The afterglows, again, give vital clues into that, coupled with the locations in their hosts. So this is another more recent example. We've been doing this for about 10 years or so, where we've been actually able to, this is just in practice, what we actually do. So each wavelength gives us information in this kinetic energy circumburst density phase space, and each wavelength on this spectrum, so if we detect it in the radio, the optical, and X-rays, it can give us a solution, essentially, and a joint solution provides us very nice distributions for the kinetic energy and density for each burst. And so we did this for a large population. The one thing I should mention is, I said we do this wild chase with observatories like the Keck observatories, some of the best observatories in the world. And we do this because the short gamma ray burst afterglows are extremely faint. They're exploding in very low density environments. They have relatively low kinetic energies compared to other stellar explosions. And so they actually have very faint afterglows. And so the detection rates have not been super great. And so these are the detection rates broken down by wavelength. So you can see only 7% of short gamma ray burst afterglows are really, really well constrained in terms of their properties. And so this is the overall distribution. So you can see for the circumburst densities, and you can just pay attention to the red line here. But this is the overall distribution and densities when putting together a decade's worth of observations of short gamma ray bursts, mapping that spectrum and trying to get the density. So you can see, again, they explode in extremely low density environments. For context, the midplane density of the Milky Way is 1 particle per centimeter cubed. This is 3 orders of magnitude below that. So again, they're exploding in isolated environments. The kinetic energy, we also can get a full distribution on that. And so just I'm hammering the point home that afterglows do a lot for us in terms of localizing the burst, getting the redshifts, and also getting fundamental properties about it. So this is some of the clues that we've learned from short GRBs and provide a great setup for what can we learn from the first neutron star mergers detected with LIGO. Are there any questions? Yes.
There must be very small probability of both kicks being the same direction.
Yes, for sure. Yeah. And so there are, yes. And so you have to go through kind of a tangled web of making sure that your neutron star binary does not get disrupted. So for sure, there are systems that started out as bound massive stars and go through that process and then get disrupted. But we know that many, a good fraction do survive that the 2 kicks, because we know of 17 galactic double neutron star systems that have survived. So they don't necessarily have to be, they could be kicked toward each other, but yeah, most often they'll probably be kicked away from each other and those will be disrupted and we'll never see them as neutron star mergers. Yeah, it's a good question. Okay, so now just to put this into context and try to explain why this has been a difficult business to find, you know, to actually do this in short gamma ray bursts and setting up for now LIGO mergers. So on axis, again, we're stuck with this orientation. When SWIFT detects a gamma ray burst, we're most likely on axis. It triggers on that gamma ray emission. And so we're staring down the barrel of the jet. We see this power law afterglow that fades over a course of a day or less. And then later, if short gamma ray bursts do actually come from neutron star mergers, we should also see this kilonova signal. We see it later because we see the fastest emission first. If we're staring down the barrel of the jet, we'll be dominated by that relativistic outflow. And that's the thing that we'll see. And any kilonova signal from our processed material, the radioactive decay, will be buried in that. And so we'll actually only see the emergence of a kilonova at later times. This is just based on our vantage point. This material is traveling at, you know, mildly relativistic speed, so we don't see it till a little bit later. And so and then again, this gives us fundamental properties of the jet. This, of course, tells us all about the origin of gold and other things that we're really excited about. Of course, you're all experts in this, so I won't go into too much detail. But as far as the observational campaigns are concerned, you know, the ground-based ones can trigger really quickly, and then the space-based is necessary at these distances to even hope to find a kilonova within that signal. So we were successful back in 2013 in doing this. This is an example of a short gamma ray burst where we tracked the afterglow over time that basically dropped like a rock as a power law. By a day after, we had no signal left. And then HST observations were triggered, and you can see this near infrared excess. I'm sorry, I didn't explain the axes. This is a brightness versus time, essentially. You can see it drops like a rock, and then this near infrared excess at about 9 to 10 days after the burst was interpreted as a kilonova. This was a several thousand second observation with HST. We had no hope of getting a spectrum to actually conclusively say that was a kilonova, but you can see, you know, this infrared excess is orders of magnitude above where we expect the actual brightness of the afterglow. And so we said that that was a different emission component. It had to be a kilonova. So we've been able to do that successfully. And now as we transition to off-axis vantage points, we now are literally looking at things from a whole new angle. And we're actually able to see the kilonova emission first, because that relativistic emission is very, you know, highly beamed. And so we actually don't see it come into view for a while. So actually it's kind of strange, but the first thing we actually see is a slower material. So we see the kilonova first. That's what we saw with 17817. And then later we'll see that afterglow as the jet starts to come into view. We'll see that later. And so it's kind of strange to wrap your head around. We're seeing the same system, but we're just seeing it at different angles. And that really changes our observing strategy and what signal we see first. This transition, at least for 17817, happened at a couple of weeks. And again, you have ground-based campaigns that dominate first. You'll see that kilonova, and then the space-based observatories will take over. This was the kilonova emission from 1708-17, compiled in Ashley Villar's paper across many, many different wavelengths. This is, again, brightness versus time, an extremely well-sampled kilonova. And then the rest of this section of the talk will be focused on what we can learn from the afterglow itself. This is just a slide in case you've been living under a rock and don't know about 1708-17. Yeah, okay, so we detected a neutron star merger, 28 square degree localization, very nearby, and these are kind of the mass ranges of the neutron stars back in, and so this is what I'll be focused on, and the long-term evolution of its relativistic outflow. So one thing that we've been exploring is the notion that this may be a structured jet. And so what I mean by that, and I kind of alluded to this earlier, is that you have this merger ejecta, that the stuff that actually radioactively decays and forms that kilonova signal that you know about. But this jet has to basically punch out of this cloud of kilonova material, and this interaction, we think, can actually be imprinted on the jet structure. And so instead of just looking down the barrel of the jet and seeing this highly relativistic emission that just power law decay, we might see something a little bit more complicated, some velocity structure in the jet. And because of our different vantage point, the fact that we're off axis from the barrel of the jet, we actually are privy to this structure for the first time. And that's really exciting and interesting because we're actually able to, understand the mechanisms and the interaction between the different outflows from neutron star mergers, and also how jets interact and are launched. But these constraints on this jet structure can only be afforded with this off-axis vantage point. And so LIGO is actually giving us a gift in terms of being able to actually see these off-axis. So I'll concentrate a little bit on the next couple of slides on the optical emission, just because that's mainly what I studied, but there have also been companion papers that I'll present in the radio and the X-ray band. But of course, measuring the optical brightness requires a really good template image. So we require that we have an image where the kilonova or the afterglow is not seen anymore, because then we can't measure the brightness very well. And so again, this was on my title slide. This is a 7.5-hour Hubble Space Telescope image that we took. Thank goodness, it's the first time since the birth of the merger that we actually don't have any more optical emission to deal with. So we can finally, write our papers and go home in terms of the optical emission here. So I'll just basically highlight the importance of templates, and this is really important in transient astronomy in general as we gear up for more advanced surveys. This is an example of a HST image taken 218 days after the merger, and this is the explosion site. Most people up until now, without a good template image, have actually been using galaxy modeling software to create a galaxy model. You subtract that model, and you get something like that. So clearly, it's an imperfect description of the actual galaxy. This particular galaxy had concentric shells, indicative of a previous galaxy-galaxy merger. So it's just much more complicated than any galaxy modeling software can produce. And you can see, you can zoom in at the location of the merger. You have this highly noisy and uncertain background and maybe a source right here. And so a lot of people, when they're modeling the optical afterglow of the source, have been relying on these galaxy models, which are imperfect, to actually extract the brightness and then do physics with that. And so now, for the first time, we have this template image. If you subtract it, you get super clean subtractions. This is, by the way, just a chip gap, so it's nothing, not real. And you can actually, get a much cleaner background. And so we did that, collecting 10 archival observations in HST, and we did that galaxy subtraction mechanism with afterglow images ranging from 100 days to 300 days or a year after the burst at the merger. And you can see a source in every single one. Of course, these are extreme, like at the limit of Hubble Space Telescope, you're also introducing noise when you do the subtraction, but this is really state of the art, the best that we can do with the afterglow. And we actually created a revised optical afterglow spanning, a year after the burst, which is pretty amazing. I keep saying burst, I mean merger, sorry. One and the same. And so this is essentially the brightness versus time. And this is the revised afterglow light curve spanning 100 to 300 days. And this is a structured jet model. So that structured jet scenario I was talking to you about, this is not a fit. So this is basically taking the best fits from the radio and X-rays, which we're also tracking this over time, figuring out what the optical brightness should be, and then putting it on this plot and seeing what would happen. And so actually it fits extremely well with the available data. And just to let you know, if we entertain the scenario that there was no jet created and it was a what we call a quasi-spherical explosion, where maybe there was a jet but it never was able to break out of that kilonova cloud, then you get this dotted line, and you can see that it's clearly not a good match for that. And so this, at least from the optical, was the first indication that there was a jet that was successful, and we also think that there was some velocity structure in that jet. Not a fit. So it's very different behavior than the power law on-axis afterglows, just because of the different vantage point. But the explosion properties, when you actually infer the explosion properties, the kinetic energy, density, the geometry of the jet, so we think of the 5-degree jet, was actually extremely similar to those of short gamma ray bursts. So it's different temporal behavior, but just because of the off-axis angle. And we think that maybe short gamma ray bursts may also have these structured jets as well. But we're not able to see them because we're only privy to the on-axis emission. And so it's comparable to short gamma ray bursts. This is a companion study that was also released by a graduate student at Northwestern, where we also tracked this in the radio and X-ray wavelengths all the way to 750 days as our latest data point. And so this was just published this past quarter, and we were actually able to see beautiful agreement. So these are structured jet models in the radio and the X-ray. So this is corroborated across the entire EM spectrum. So this is like an extremely beautiful data set of this merger. We're very excited to see the first non-detection, so because then we can again go to sleep. But one thing, twist to the scenario is that if the neutron star, so we don't actually know the remnant of GW17, so we don't know what it formed. We don't know if it formed a hypermassive neutron star or a black hole, or if a neutron star formed at all, and then for any significant period of time. And so if a hypermassive neutron star did form, at least for a significant amount of time, so beyond a few milliseconds, that spin down, and it was rapidly spinning, that spin down energy could be imparted to the surrounding medium and actually basically accelerate a shock around the neutron star merger remnant and actually produce synchrotron emission. So that synchrotron emission, we think, is mainly dominant in the radio bands, but there could be some X-ray contribution. And so that we call it hypermassive neutron star remnant signal could actually, these are various models based on different parameters, but you can see now we're starting to, with our first upper limits, constrain the presence of a hypermassive neutron star at the end, because implications for the equation of state and all of that stuff. And so maybe it could come back. We don't really know, but we're going to keep looking. So the long-term evolution, this is the last slide on just the rate connecting the radio to the X-rays, but you can see from 100 days all the way to 580 days. This is now a spectrum. This is flux versus frequency. This is actually even simpler than short gamma ray bursts. They're actually all on the same power law, the synchrotron spectrum. And so that's great in the sense that you can predict, from one or two of these wavelengths, you can predict what the other flux will be. So that's extremely simple. The bad news is that each of those power laws has a different mapping to those, the kinetic energy, the density, et cetera. So you actually have huge degeneracies because each new wavelength doesn't provide too much extra information. And again, this is just the power law index over time, and they're all on this spectrum. And so this is kind of an interesting feature of 17817. We don't exactly know why all of the wavelengths seem to appear on this spectrum versus short gamma ray bursts, but that could just be a product of when we're actually seeing the merger, like very, very late in its evolution. So what's really interesting now, connecting the two populations of short gamma ray bursts and mergers. And so this is the short gamma ray burst optical afterglows. This is optical brightness versus time. You can see these power law decays. And then we have a couple of short gamma ray bursts which have what are called jet breaks. And so this is essentially a temporal steepening in the light curves that indicates that there's actually a jet, that there's actually some collimation. And so this is an example of a temporal steepening, a short gamma ray burst that had a temporal steepening here. But essentially, you see either a single power law or a temporal steepening there. And if you actually extrapolate and because we're all luminosity, oh, this is the kilonova, just so you can see the 17.70 kilonova. It's generally fainter than the luminosity of the short gamma ray burst. So if you actually extrapolate the short gamma ray burst luminosities down to where we would actually hope to see 170817's afterglow, basically if 170817 was on axis, we should have seen it this bright. However, it was about 30 degrees off axis, so we actually see it down in this regime. And if they actually have very similar properties that govern their temporal evolution, then 170817 should fall somewhere in this window. And in fact, that optical afterglow light curve I showed you is right there now. So it's a tiny little blip, and it's extremely faint in luminosity, but basically is perfectly connected and easily extrapolated back to the short GRB population. So what this is telling us is that the combination of explosion properties, again, the kinetic energy densities, et cetera, from these cosmological distant events very far away, are the same as the one that we saw right in our own cosmic neighborhood. So in some sense, that's no surprise. We expect neutron star merger outflows to be universal across the universe. It also tells us that because we don't have definitive evidence that short gamma ray bursts came from neutron star mergers, this is another piece of evidence that the explosion properties seem to match extremely well. I will be very interested to see where the first neutron star black hole, if we get the first neutron star black hole and its afterglow, where that lies in this diagram, because one of the open progenitors for short gamma ray bursts are neutron star black holes too. So understanding their outflow properties will be really interesting. Okay, let's see. So despite very different temporal behavior, we think they have very similar explosion properties and jet geometry, and this is telling us that for the first time. And then the primary difference is viewing angle. So we're literally just seeing the same thing at an angle. Okay, and I always like to give this slide because I haven't seen a good kind of summary of all of the observations of 170817 in terms of timeline. And I always get confused, especially the optical and near infrared band. And so in the optical and near infrared, the community detected the kilonova at about 10 hours after the merger. They followed this until about 20 days or so. Then the sun got in the way, which was very annoying. It resurged after 100 days after the merger. By then, the kilonova had dropped and the afterglow had taken over. It was, a fairly weak signal. And so that's where all the HST observations came in. We were able to map that till about a year after merger and get all that exciting thing. And then have a deep template at 580 days. And basically, we think that's the end of the story with the optical band. In the radio, actually, we successfully were able to trigger observations that night following the kilonova detection. So we got so these downward arrows are upper limits at 13 hours, and then it was first detected at 16 days and has been ever since. And finally, at 740 days after, there's no radio emission. Good. We'll see what the future leads. And then this is just the X-rays. Again, we had a deep upper limit. I think this is actually really remarkable. I mean, this is a space-based observatory. So this was a Chandra X-ray observatory. And the program was triggered to happen basically on a weekend. So we always joke that the best transients happen on Friday nights because it basically ruins everyone's weekend. But the Chandra staff worked really hard to get this very deep upper limit, and then saw the rising emission in the afterglow. The sun got in the way, and then the sun got in the way here, but it's not as much of an issue in the radio band. And then it's still going on. And so this is where we're at so far with the EM emission. So open questions going forward in this regime. Will future neutron star mergers have similar behavior? What about neutron star black hole mergers? Then can we find signatures of jet structure in short gamma ray bursts on axis? So I have a couple of slides on the next two, on each of the next two, and we'll go through those. And so this is a bit of a transition. And so I want to actually go into constraining the actual origin. So not just the outflows from the mergers, but actually constraining how that binary neutron star was formed to begin with. And in particular, I want to go into a mechanism called a dynamical origin that occurs in globular clusters where you can have exchanges and things like that. So what this template did basically is once we subtracted off the galaxy light, was it afforded us a very deep constraint at the position. So you can see there's nothing there. And one of the things that we can do with a static image is actually place constraints on globular clusters. And so these are dense star clusters, 100,000 to 1 million stars. And this is just an example. And we're able to actually get so far down the luminosity function of these that we can rule out a globular cluster. This is important because it's been proposed that neutron star binaries can actually form dynamically in these clusters via exchange interactions. These are very dense stellar systems, so there can be lots of things going on, exchanges, captures, etc. And so this type of mechanism has been used to explain binary black holes, and so why not binary neutron stars? But this is actually showing us that this is basically impossible for 17817. So this is the globular cluster this is the mass function of globular clusters. So this is mass, and then this is the cumulative probability. This is the globular cluster mass function for this host galaxy, NGC 4993. And our limit is so deep that we can essentially rule out any reasonable amount of parameter space in the globular cluster mass function. So the median globular cluster mass is something like 200,000 solar masses, and our limits go as deep as 13,000 solar masses. And so this is a really direct and deep constraint on a what we call in situ dynamical origin. So basically, it didn't form and merge in a globular cluster. It would be, we can place limits on that. Just to show you short gamma ray bursts, they occur at cosmological distances. So the constraints that we can place on this are much less stringent. So basically, we cannot place any meaningful limits on the globular cluster, presence of globular clusters. But this is a game that we can definitely play in the era of LIGO mergers. This is the first direct and deep constraint on a dynamical origin observationally. And this is great because it basically rules out a channel, a viable formation channel that has been proposed as a mechanism to explain neutron star binaries, at least at the 10 to 20% level. We've also been doing this on the theoretical side. So this is work done with Clarier at Northwestern, and basically trying to understand theoretically, okay, well, the next neutron star merger, will it be worth trying to find a globular cluster at that position too, and trying to place any constraints on the dynamical origin. And what we found was actually the presence of black holes in your globular cluster has a really big effect on the encounters between neutron stars. And so these are two snapshots of a simulated globular cluster. The orange dots are neutron stars. The black holes are the blue X's. And you can see this is one cluster with many black holes that have, due to mass segregation, the heaviest things sinking to the center. All the black holes have basically clustered in there and prevented the neutron stars from actually sinking in as well, and basically kept the neutron stars at more dispersed locations. Whereas if you only have a small number of black holes, so in this case you only have one black hole, the neutron stars can actually hope to sink toward the center, undergo more encounters, and form more neutron star binaries and more mergers. And so the effect of black holes is actually really important in trying to understand this. And so that's just one snapshot of a globular cluster with black holes and without. And so what she did is she ran 144 Milky Way-like models of globular clusters and tracked them over their full 14 gig year evolution. And then she tracked any binary that was formed, whether it be in the merger, or sorry, in the cluster, or if it was ejected due to neutron star kicks. And so this is what she came up with, and this is kind of confusing plot, but it's ordered by time, formation time. And so this basically tracks each system as essentially, this is the time of formation and this is the time of merger. And you can see just the upshot is that you have so many binary black holes for a range of formation time scale. So globular clusters are a great formation mechanism for binary black holes, but there's only a handful of neutron star black holes and a handful of neutron star binaries that ever hope to merge in a globular cluster, or they were formed in the cluster and then merged outside. And so these are the overall rates. And so you can see compared to this is merger rate versus redshift, this is just very local. You can see that LIGO neutron star mergers and the upper limit of LIGO neutron star black holes are about 4 orders of magnitude higher than the rates from globular clusters that Claire calculated. And so this is one of the first studies that has actually definitively shown that globular clusters are not actually, playing a viable role in terms of formation. Okay, and I just wanted to show this rate. So basically putting all the rates that we have, and in light of also that second neutron star merger that I'll allude to in the last couple of slides. But these are basically all the rates put together. So the observed short gamma ray burst rate is somewhere around 10 per gigaparsec cubed per year. If we include effects for beaming, the fact that they are beamed probably in 10-degree jets or so, the actual rate is somewhere up here. We also have a galactic double neutron star rate, so extrapolations on the galactic double neutron star rate out gives us a handle on the volumetric rate. And then we have LIGO's first observing run gave us a nice upper limit, the fact that we didn't detect anything. And now, 2 neutron star mergers later, 2 observing runs later, we actually have a really nice gravitational wave rate from neutron star mergers that fits in line with all of these. And this is the latest rate just of last week. And so you can see that basically there's all these kind of uncertain rates, but LIGO is making huge progress only with 2 events in understanding the rates. One of the big questions, of course, is do all neutron star mergers produce relativistic outflows? This could also tell us a lot about the kilonova structure as well as the equation of state of what actually is causing the jet launching. Okay, 2 more slides, I think. So this is basically O1 and O2 so far. So I'm sure all of you have seen this. Basically, this is just the distribution of masses of binary black holes and distributions of LIGO Virgo neutron stars. And you can see 10 binary black holes in the first 2 observing runs and 1 binary neutron star. Now we have, so far in O3, we have 31 additional binary black holes, which is incredible. And between 1 and 3 neutron stars, only 1 has been confirmed as a real signal, but 3 have been basically announced and are publicly available as candidate neutron stars, binary neutron stars, and then 2 unconfirmed neutron star black holes. So the big result from last week was 190425, the second binary neutron star merger. Unfortunately, it was a single detector event, so it basically covered 20% of the sky. So it made it basically impossible to get any meaningful electromagnetic follow-up compared to the 28 square degree localization of 170817. So this is essentially one of the lobes of the sky map imprinted on a sphere. And so it was also more distant. So it was, several times more distant. So compared to the 40 megaparsec distance of 170817, it was 160. One thing that's really interesting is that it has a very high total mass. And so compared to 170817, which had a total system mass of 2.7 solar masses, this has a total inferred mass of 3.4. This is just putting that into context also with the galactic binary neutron star systems. So this is from this LIGO paper. You can see the probability density versus total mass. These are basically for different spin priors on the neutron stars that give these, different orange and blue histograms. But for this system, you can see it's several sigma above the galactic distribution. If you fit the 12 or so known merging systems with a Gaussian, then you actually get that there's several sigma above. So trying to explain this gap is going to be really interesting. People have raised so far maybe a different formation mechanism, but I just told you that it's hard to produce these dynamically. Also, there could be something that we have to revisit in terms of common envelope and mass transfer to actually try to explain this really, really heavy system. So I'm excited, and so I'm sad that we didn't actually get any EM follow-up meaningfully, but I'm excited that we're actually, there's something really new and interesting about this system. I'm going to skip this. These are just proof of concept things. Okay, so this is kind of just final thoughts in terms of looking forward and the future ahead. So I think 17817 really pushed the limits of current observatories. It was at 40.7 megaparsecs. I showed you, hundreds of hours worth of data, just on that event alone. It was an extremely local event. And beyond O3, so beyond this current observing run, we'll rely really heavily on extremely large telescopes as well as James Webb, which I'm super excited about, in order to characterize these signals. And the radio and next generation facilities, which are planned or under construction or just starting their commissioning phases. And then the X-rays, we really have to think carefully about what we want to plan in the future. Or we will hope maybe that neutron star black holes have more luminous afterglows that might give us a leg up on trying to understand and characterize their signals. This is a shameless plug because I know that some people here are interested in delay time distribution, so I put this up. But basically, I showed you that short gamma ray burst distribution of redshifts. And so we're now actually doing our due diligence and following up every single short gamma ray burst, trying to find redshifts for all of them. And we're finding actually a growing population of higher redshift short gamma ray bursts between redshifts 1 and 2. That will have implications for delay times. But this is just a placemat of all the short gamma ray burst locations that we've followed so far. Okay, so this is my final slide. So I've talked basically about relativistic outflows. I showed evidence for narrow jet production, that neutron star mergers and short GRBs have similar explosion properties. And so I'm interested in what the future holds, and can we find signatures for jet structure in short GRBs? I also showed some results in dynamical origin. So there's direct observational constraints as well as theoretical constraints on this question now. And then are there exotic formation scenarios that potentially could explain 1904-25, that new one? And finally, the biggest open question, what surprises lie ahead, which I'm most excited about. So thank you. Sorry. Hold on.
So, one thing I didn't understand on the blog was, we were comparing the merger rate from LIGO merger rate that in globular clusters. Is that merger rate per globular cluster or per galaxy?
That was per unit volume there. Yeah, that was per unit volume. So this rate, yeah, it wasn't per globular cluster. Here. Yeah, so this is a volumetric merger rate. So essentially to get to this, we had first a per globular cluster rate, and then we assumed a density distribution of globular clusters, for instance, in the Milky Way, and then we got the rates that way, the volumetric rates. Yeah. Yes. Yeah. Yeah, and so the properties of there are many more clusters. The properties of those clusters are for the intents of forming dynamical encounters, interactions, are largely similar. So for instance, things that you'd care about, like the mass function, or how dense each globular cluster is going to be similar. And so what the overall number of globular clusters won't matter too much as long as you assume that the densities of globular clusters within your galaxy is similar. So even if you dialed up your globular clusters densities by 4 orders of magnitude, which is unrealistic, you still would only be touching the rates. Yeah, but I think the absolute number of globular clusters per galaxy wouldn't matter in this case. It is already taken into account.
See what you said, roughly the ratio of the number of neutron star mergers to black holes is 1 to 10 or so. Now, but you see, I misunderstand this graph. I've seen some neutron star black hole mergers.
Oh yeah. So there are. Where did I put my thing? Yeah. So here, like this graph, you mean? So there are neutron star black holes, and here, sorry, I didn't put it in, but they're basically the neutron star black hole rates are by these red and blue lines, and they're about the same. So we see comparable numbers, but equally low of neutron star black hole. Mainly because of the lack of neutron stars that are allowed to have dynamical interactions. They generally either get kicked out early in the evolution, or they're prevented from mass segregating to the center. Yeah. So they had limited follow-up. So there are 2 others that at least have a greater than 50% chance of being a neutron star binary, and then at least 2 that have a greater than 50% chance of being a neutron star black hole. And those have not been released. Their masses have not been released, and spins, and et cetera. So 1904-25 is the only one for which we have information on the mass, public information on the masses and spins. Yeah. So I'm not part of LIGO, so I actually don't know that information, but there was electromagnetic follow-up for all of them and no counterparts. Uh-huh. Yes. Yeah. Mm-hmm. Yeah, right. So I think, I forget the exact parameters, but at least one of these was something like 1.6 or 1.7 was the median for that mass, for one of the components. For this event? Yeah, and so this was released just last week, the discovery paper on this. Yeah. So actually, it's the archive number. Yeah. But it's just hot off the press from last week at AAS. So yeah, so I encourage you to go here. This is kind of the main takeaway, the main big result, just because the EM, the localization precluded any meaningful follow-up. No, yeah. So there is no short gamma ray burst associated with this. But granted, 17.17's gamma ray short gamma ray burst was just at the limit of the Fermi detector, and this was, a few times farther